In this video, we're going to explore the relationship between free energy, delta G, and equilibrium to take a look at how spontaneity and reversible reactions relate to one another. First of all, just a review from equilibrium chemistry. When Q is less than K, then that means you're going to shift to the right. So that means the forward reaction is spontaneous. If the forward reaction is spontaneous, that means delta G for that forward reaction is a negative number. If Q is less than K, then that also means that the ratio of Q to K is less than 1. So that means the natural log of Q over K is less than 0. When Q is greater than K, then that means the reaction is going to shift to the left, which means the reverse reaction is the spontaneous one. So that means delta G for the forward reaction is greater than 0. So also, the ratio of Q to K is greater than 1, which means the natural log of that ratio is greater than 0. When Q happens to be K, you're at equilibrium. So neither the forward reaction or the backward reaction is spontaneous, so delta G is just 0. And the ratio of Q to K is 1, which means the natural log of that ratio is 0. Now the reason I'm doing that is so we can start to put this together on a graph. Let's say we have a graph space where delta G is on the vertical axis, that's free energy, and the natural log of Q over K is on the horizontal axis. Remember, when the ratio of Q to K is 1, the natural log of the ratio of Q over K is 0, so that puts us at a point in the very middle. We also saw that when delta G is negative, in other words, when the forward reaction is spontaneous, the natural log of Q over K is less than 0. So that gives us a line that extends into the negatives on both axes. And also, when delta G is positive, in other words, when the forward reaction isn't spontaneous, when the reaction is shifting to the left, the natural log of Q over K is greater than 0, which means that we can extend that line up into the positives on both axes. So there's a straight line relationship that turns out to be present between free energy and the natural log of the ratio of Q over K. And the slope of that line turns out to be R times absolute temperature. So looking only at one quadrant here, we could make the equation for that line. Delta G is R times T times the natural log of Q over K. Or just using the rules of logs, we could rewrite this as delta G equals RT natural log of Q minus RT natural log of K. Now let's think about what is Q at standard conditions. Q is either going to be pressure of products over pressure of reactants, or if it's QP, QC could be concentrations of products over concentrations of reactants. But if you're at standard conditions, the pressures are all 1 atmosphere, so that means that would be a 1, and the concentrations are all 1 mole per liter, which means that would also be a 1. So Q at standard conditions is 1. So in this relationship we have here, this term would be RT natural log of 1, but the natural log of 1 is 0. So that term goes away when you're at standard conditions. So delta G naught is just that term. So a question arises, how does delta G compare to standard delta G when you're at non-standard conditions? And the answer is found in using that equation. Let's look at some hypotheticals. Let's say we have A2 reacting with B2. These are just generic, not real reactants. And they're in equilibrium with 2AB. We have a little particle key here. And here we have 3 different situations. And let's pretend that each particle represents 0.1 moles. And let's pretend that the space represents 1 liter. If A represents the equilibrium conditions, then what is K? Well, we've got 2 particles of A2, so that represents 0.2 moles per liter. And we've got 2 particles of B2, that represents 0.2 moles per liter, and that's in the denominator because they're reactants. And AB we have 1, 2, 3, 4 particles, so that represents 0.4 moles per liter. So since the equilibrium expression would have the numerator squared, because the coefficient on AB is 2, this would be equal to K, because it's at equilibrium. We've established that. So that turns out to be 4. So K for this reaction is 4. The next question is, which mixture has the highest delta G? Well, for A, delta G is 0. And we know that because it's at equilibrium. It's not spontaneous in either the forward reaction or the reverse reaction. Let's look at the other two. Well, let's look at B. We have 2 particles of AB. So the numerator is going to be 0.2 molar squared. And we've got 1, 2, 3 A2 and 1, 2, 3 B2. So the denominator is going to be 0.3 times 0.3. And that's Q. That's what we're calculating here. And Q, if you work this out, turns out to be 0.44. So what is delta G? Well, using this formulation here, delta G is delta G naught, which is given to us here, minus 3.4 kilojoules per mole, plus R, let's put this in kilojoules, 0.008314 kilojoules per mole Kelvin, times temperature. Let's assume that it's 298 kelvins, kind of room temperature, times the natural log of what we just calculated to be Q, which is 0.44. And if you work this out, you get negative 5.4 kilojoules. So this reaction is spontaneous in the forward direction, which makes sense because Q is 0.44, which is less than 4, which was our value for K that we calculated earlier. Now let's look at C. For C, Q is, in the numerator, we're going to have 1, 2, 3, 4, 5, 6 ABs, so that's 0.6, and that, remember, is squared. And we've got only 1 A2 and 1 B2, so that's 0.1 times 0.1 moles per liter. If we calculate this out, we get 36. So value of delta G is delta G naught, negative 3.4, let's leave the units off, plus R, 0.008314 kilojoules per mole Kelvin, times the temperature, 298 kelvins, times the natural log of 36, which we just found for Q. And this comes out to 5.5, and the unit would have been kilojoules. Delta G is positive here, so that means the forward reaction is not spontaneous, which goes along with the idea that Q is greater than K, which means the reaction is shifting to the left. Next question, is the reaction spontaneous when A2 equals B2, and that is also equal to AB, and all of those are 1 molar? So in this case, Q is going to be 1 squared over 1 times 1, and that's just 1, which means the natural log of Q is 0, which means that term just disappears, and so the reaction has a delta G that's equal to delta G naught, and that's negative 3.4 kilojoules per mole. If we want to find K, here's where we're going to start. We know that delta G naught is equal to negative R times T times the natural log of K. So if we divide both sides by negative R times T, we get negative delta G naught over R times T equals the natural log of K. So that would mean that K, if we take E to both sides, would be equal to E to the negative delta G naught over R times T. So at 298 Kelvin, we can use the standard G naught value here, which tells us that K is equal to E to the negative 141,000, let's keep our units good, joules over 8.314 joules per mole Kelvin times 298 kelvins. When you calculate this all out, you get 6.6 times 10 to the 24th. So that's our value at 298 kelvins. At 973 kelvins, we're not going to be able to use that value. However, we do know that delta G naught is equal to delta H naught minus T delta S naught at other temperatures. And so in this case, that's negative 198,000 joules minus our temperature of 973 kelvins times negative 187.9 joules per Kelvin. And that gives us a delta G naught at this temperature of negative 15,600 joules. So at 973 kelvins, we'll just reapply this. K is equal to E to the minus 15,600 joules divided by 8.314 joules per mole Kelvin times now 973 kelvins. This comes out to 6.87, which is a substantially lower number. So that means there's less product at equilibrium, even though the rate is higher. So if you tried to use this as a practical strategy, you would probably have to continually remove product to cause a reaction to do a Le Chatelier shift to the right to be practical. Here's the same reaction again. And here we have a direction of spontaneity question. We have two sealed containers. They're filled with 0.5 atmospheres of SO2, 0.01 atmospheres of O2, and 0.1 atmospheres of SO3. One's put in a 298 Kelvin water bath and the other one's in a 973 Kelvin water bath. Which direction will the reactions proceed at each temperature, if they will? We can get the answer to this question by asking ourselves what is delta G for each of these reactions. Remember that delta G is equal to RT natural log of Q minus RT natural log of K. Or we could simplify this, just pull the RT out. RT times natural log of Q minus natural log of K. And then we can just do this at both temperatures. So at our 298 kelvins, delta G is equal to 8.314 joules per mole Kelvin times 298 kelvins. And then we have to know what Q is here, because we're going to multiply this by the natural log of Q minus natural log of K. So let's figure this out. The reaction, remember, is SO2 plus O2 makes SO3. There's 2 in front of SO2 and SO3. So Q is going to be the pressure of SO3 squared over pressure of SO2 squared times pressure of oxygen. So this is 1 atmosphere squared over 0.5 atmospheres squared times 0.01. And this works out to 400. That's Q. So we're taking the natural log of 400 here, and then we're subtracting the natural log of K. Remember, we just calculated that K at 298 kelvins was 6.6 times 10 to the 24th. And so when we calculate this all out, we get negative 127,000 joules per mole, or negative 127 kilojoules per mole. Let's do the same calculation at 973 kelvins. I'm going to leave the units off this time. Still 8.314 joules per mole Kelvin. Now our temperature is 973. The natural log of Q is still the same, 400, minus the natural log of K. But at 973 we had calculated that K was 6.87. So that means we're going to have a positive 32,900 joules per mole, or 32.9 kilojoules per mole. Okay, so at the low temperature, delta G is negative, which means the reaction is spontaneous in the forward direction. It's going to shift in the forward direction. At the high temperature, delta G is positive, which means the reaction is not spontaneous in the forward direction, so it's going to shift in the reverse direction. Here's another view, kind of a graphical view. On the horizontal axis here, we're going to have a graph that has possible values of Q. And one extreme would be pure A, and the other extreme would be pure B. And right in the middle would be when the concentration of A and the concentration of B are the same. So this is for a simple generic reaction where A is in equilibrium with B. Now, if delta G is less than 0, there's a relationship between K and delta G. And we can get that by solving for K. We've done it before. K is equal to E to the minus delta G naught over R times T. And then if we think about the fact that if we put delta G naught on the horizontal axis and we put K on the vertical axis, this function is going to give a graph that looks like this. And that crossing point there is at 1. So that means if delta G is less than 0, K is greater than 1, and if delta G naught is greater than 0, K is less than 1. So in the case that we have here where delta G naught is less than 0, in other words, the G at A compared with the G at B is a decrease, then K is going to be over on the right-hand side of 1. And the lowest spot on this graph is going to be sitting closer to the product side than to the reactant side. And you can sort of think about this free energy graph like a little ramp. And if you start out with a Q that's over here, represented by this ball, well, that's going to roll down towards that bottom part of the ramp. Or if you start out with a Q that's over here, that's going to roll down to that bottom part of that ramp. And the only time you're not going to get any movement, any shift to either the left or the right, is when you're right at K. You can make that same argument for if delta G is positive, then K is going to be sitting on the left-hand side of Q equals 1, right in the middle there. And so most of the time, you're going to have the reaction shift to the left. Sometimes it would shift to the right, but there are far fewer values of Q that would cause the reaction to shift to the right. And if K is equal to 1, then you're right in the middle there, and that's going to be the spot where you always end up. So reactions proceed towards the minimum value of delta G. One last thing. Let's think about free energy and solubility of substances that dissolve partially in water or some other solvent. When a substance dissolves, but delta H is positive, so that means this is an endothermic reaction. It would feel cool to the touch. Energy is being absorbed by the system as the dissolving takes place. What must be true about delta S? And from a qualitative standpoint, we can think about the fact that endothermic reactions tend not to be spontaneous. So if this actually dissolves, what must be true about delta S is that it must also be positive. An increase in entropy, if it's big enough, can offset the fact that this endothermic reaction would be unlikely to occur spontaneously. Here's a different question that's kind of related. When a substance doesn't dissolve, but delta H is less than 0, so it's exothermic, which tends to be spontaneous, what must be true about delta S? Well, if this endothermic reaction does not occur spontaneously, then that means that delta S must be a negative number. In other words, there's a decrease in entropy such that the reaction will not occur spontaneously. Let's look at a quantitative example. Here's calcium chromate dissolving into calcium ions and chromate ions. KSP for this reaction is 7.1 times 10 to the minus 4, and delta H is given here as negative 26.6 kilojoules. What can we conclude about delta S? Well, one thing that we can conclude just qualitatively is that since delta H is negative, it's exothermic, but KSP is pretty small, that means that the value of delta S is probably negative. But we can figure this out quantitatively as well. Here's how that would work. We know that delta G naught is equal to minus RT times natural log of K. And we also know that delta G naught is equal to delta H naught minus T delta S naught. And we want to find out what delta S naught is. One step towards doing that would be to set these two equal to each other. So negative R times T times natural log of K equals delta H naught minus T delta S naught. Remember, we're trying to isolate delta S, so let's add T delta S to both sides. So So that would give us T delta S naught equals, and then let's also add RT natural log of K to both sides. So that would be delta H naught plus RT natural log of K. Let's divide all the way through by T to eliminate T. So now we get delta S naught isolated, which was our objective here, is equal to delta H naught over T plus R times the natural log of K. So now let's plug numbers in here. Delta S naught is, our delta H value was negative 26,600 in joules. Our temperature, well, this is standard, so we're going to use 298 kelvins, plus R, 8.314 joules per mole Kelvin. This should probably be joules per mole here. Times the natural log of our K value, which is our KSP of 7.1 times 10 to the negative 4. And when we work the math out here, we will get a value of negative 149.5. The units are going to be joules per mole Kelvin, which is a good entropy change number. Now, the fact that this is negative confirms what we thought through qualitatively and shows us why the value of KSP is small and this substance doesn't dissolve very well.